All right. So we have spent the last few weeks characterizing the motion of objects, and one limitation that we have in that portion of the course is that we have to be told pretty much everything about the motion to be able to solve for what's going to happen to an object. And so, what we're going to turn to now is we're going to start to understand and analyze why the motion of an object might change. And that is tied to this idea of forces. So, a new physical quantity we're going to introduce is the force. So, what makes an object accelerate? Well, the forces that act on an object essentially determine whether or not an object accelerates. And so, what do we mean when we say force? The simplest definition for a force is just a push or a pull. And our forces are vectors, and so we would represent a vector just like any other vector, the force vector, just with an arrow. And our SI unit for a vector is the Newton. And this Newton is equal to a kilogram meter per second squared. So those are the units of the force unit Newton. Now, where do forces come from? In the simplest sense, forces come from contact with another object. So if there's a force being applied to an object, it must be because something is pushing or pulling on it. The one exception to that in 101 is gravity. Gravity is the only force that we are going to deal with that doesn't require physical contact. That is to say, the Earth, by being in proximity to a ball, to an apple, to anything near the surface of the Earth, just being close to those objects, the Earth pulls through the force of gravity on the object, no contact required. So gravity is what's known as a long-range force. And so there are a variety of long-range forces that we talk about in physics, but in 101 we're restricting ourselves only to the force of gravity as a long-range force. So what this means is that if you're trying to analyze the forces on an object, the only forces you can get are the force due to gravity and then contact forces between your object and anything else in the problem. So some common forces that we're going to use in 101. The first one is the force of gravity, which we call the weight. And this force points towards the center of the attracting body. So when our problems are on Earth, the force of gravity on your object points towards the center of the Earth. We typically use this lowercase w for the weight vector to designate this force. Another very common force, and again, weight is a non-contact force, so it's a long-range force. Friction is a very common force that we'll see in 101. Friction is a force between two surfaces in contact. Friction is always parallel to the surfaces in contact. We designate friction with this lowercase f, and it turns out there's a variety of types of friction. There's static friction, so when the two objects that are in contact are not in motion relative to each other. We've got kinetic friction. That's when the two objects are in relative motion, relative to each other. And then we also have rolling friction. So when something like a wheel or a ball is rolling on a surface. So we'll spend more time discussing friction later. Another common force, similar to friction, is the normal force. The normal force is a contact force between two surfaces that is perpendicular to the two surfaces in contact. So friction is parallel, a force parallel to the surfaces in contact. Normal is a force perpendicular to the surfaces in contact. We use a lowercase n to designate the normal force. Tension. So anytime you've got a rope, a string, a chain, you have the potential for there to be tension in the problem. So tension is a pulling force, and we use the capital T to designate tension. We've also got spring force. So if you happen to have a spring in your problem, there will be some pulling or pushing force corresponding to the spring either being compressed or stretched. And eventually we're going to characterize that with something known as Hooke's law, the force exerted by a spring on an object. And then our last common force that we'll see, although there might be a few others occasionally, is the drag force or air resistance. And so this is the force associated with an object moving through a fluid, so a gas or a liquid. And there's no sort of special notation for that, so maybe just F sub d for our drag force. Since force is a vector, everything we know about treating vectors translates to force analysis. And so I've got this picture down here. I've got a person pushing to the right with F1 force, a person pushing up with F2 force. The total force, the resulting force, we just use the tip-to-tail method, and the resulting force is along that axis. So typically with forces, rather than talking about resultant or total, what we're going to use instead is net. So net just means total or resulting. So if you've got multiple forces acting on an object, the net force is just the sum of all the individual forces. And if you want to use shortened notation, you can use the summation symbol to designate that we're going to add up all of the vectors to get the net vector. Okay, so one of the most useful tools that we are going to use as we begin to investigate forces and analyze the forces that are exerted on an object is something known as a free body diagram. And so a free body diagram is our way of sort of starting the analysis of forces. It is a way to visualize and catalog the forces that your object is being subjected to. And so you can read this little box from the book, but I think it's probably easier just to go through one of these examples. So down here I've got a block sitting at rest on a table. And so a free body diagram, we put that together to identify all of the forces acting on our object. So in this case, if my object is the block and I want to identify all of the forces, the first thing I'm going to do for my free body diagram is I'm going to create a coordinate system. So I've got my traditional coordinate system, x is to the positive, x is to the right, positive y is up. And then what I want to do is I want to represent the object with a dot. So my box or my block here is just this dot. And now I'm going to draw all of the forces that are being applied to my block. I'm going to draw them from that center dot. And so this is a simplification, right? I'm treating my extended object as just this dot. In future chapters, we will then expand this model to be to treat extended objects, and then we'll have a more robust treatment of the analysis of the forces that are acting on an object. But for now, we're treating our object as just a dot. So the technique here for identifying forces is really straightforward. So you'll see I've drawn this dotted line around my object of interest. And remember, the only way you get forces is if there's contact with your object from something else, right? And so when I draw this dotted line around my object, the only thing that's in contact, the only thing that my dotted line has to cut through is the table. And so the table is in contact with my block, so there must be a force associated with that contact. And in this case, it's a force in the positive y direction, and it's the normal force. Now, remember, most of our forces require contact, but there's one that doesn't require contact, and that is the force due to gravity, or the weight. And so this block is near the center of the Earth, or is near the Earth, the surface of the Earth, so there is a force down that's equal to the weight of the object, or the force due to gravity, based on the fact that the Earth is near the block. And so that force is down. And we haven't talked about Newton's laws yet, but since this object is at rest, it turns out that these two forces the normal force up and the weight down, they must be equal in magnitude, since those are the only two forces acting on our object. Another example for a free body diagram over here. Now I've got my block on rest, block at rest, but now it's on a ramp. And so I do the same thing, circle my object, and then I have my coordinate system here. And just like we've done in lab, when you have a ramp, it makes the most sense to align your coordinate system with the ramp. And so plus x for me is up the ramp, and plus y is perpendicular to the ramp. And so now I'm going to identify forces. Well, again, I circle my object, and the only thing in contact with my block is the ramp. And so I've got two surfaces in contact. I've got the potential for normal force and friction force. And then I also have, of course, this block is on a ramp near the surface of the Earth, so there's also the weight straight down towards the center of the Earth. So my first force over here is the weight. Remember, I've drawn my block as just a dot at the center of my coordinate system. So I've got the weight down. And then remember, normal force is perpendicular to the surface, and so the normal force is going to point that way. And then you'll notice in this particular problem, I also have a friction force pointing up the ramp. Now, how did I know that the friction force must be part of this problem? Well, because without the friction force, get rid of this. If you don't have the friction force, then when you look at this weight vector, some of the weight vector is pointing perpendicular to the ramp, but some of it is pointing parallel to the ramp, down the ramp. And so if you don't have this friction force, then the weight down the ramp is going to cause the block to accelerate, and it would not be at rest. So there must definitely be friction pointing up the ramp. The typical next step for a free body diagram is that when you have a vector that is not along your x or y axis, we immediately break that vector up into components so that all of our vectors on the free body diagram are just x and y vectors. So we replace the weight with a y component and an x component. Okay, with all of that background, we're actually ready to start to think about Newton's laws. So we've got three laws that essentially allow us to analyze and characterize the forces and the accelerations that an object might be exposed to, and then the accelerations that the object might experience. So Newton's first law is worded a bunch of different ways depending on where you read it. Oftentimes it might be said an object at rest stays at rest, or an object in motion stays in motion unless acted on by a net force. So this is what the book includes. The basic idea is that an object in uniform motion, so uniform motion could mean velocity, so that's constant velocity. So velocity equal to 0, the object would be at rest, or non-zero, the object moving at some constant velocity. Then if an object is in uniform motion, it will stay in uniform motion forever, right? It will remain at that initial velocity forever unless acted on by a net external force. So what this means is that if the velocity is constant, that is, the acceleration is 0, we know that the net force on the object has to be 0. Or conversely, if the net force on the object is 0, we know automatically that the velocity must be constant. So this first law, if we know something about the velocity of the object, that tells us something about the net force on the object, and if we know something about the net force on the object, that tells us something about the nature of the velocity of the object, if the velocity is changing or not. So Newton's first law is related to when the velocity of the object that you're interested in, when that velocity is constant. So what if velocity isn't constant. That is, the net force isn't zero. So what if there is a net external force acting on your object? So that brings us to Newton's second law. So Newton's second law relates the net force acting on an object with the acceleration that object experiences. And so you may be familiar with Newton's second law as F equals ma. Really, we want to think of Newton's second law as a way to characterize the acceleration an object experiences based on the net force that the object is exposed to, and that acceleration is proportional to the net force, and it's inversely proportional to the mass of the object. And so remember, net means add up, so if you add up all the forces acting on an object, that will equal the mass of the object times whatever the acceleration of the object is. So I've got a little example here. So let's say that I can push with a force of 5 newtons, and let's say I'm pushing to the right. So in my coordinate system here, my push would be plus 5 newtons in the I-hat direction. So let's say I've got 2 objects. Mass 1 is 5 kilograms, mass 2 is twice as massive, 10 kilograms. So if I push with the same 5 Newton force on both of these objects, well, the acceleration of object 1 will be 5 Newton divided by 5 kilograms. The acceleration for object 1 will be plus 1 meter per second squared in the I-hat direction. Object 2 is twice as massive, so I push with the same amount of force, twice the mass. I get that object 2 accelerates at plus 0.5 meter per second squared in the I-hat direction. Right, so not only is the acceleration dependent on how much force is being applied, but also the mass of the object. So since forces are vectors, the Newton's second law force equation is really 3 separate equations. So the net force in the x direction equals max, the net force in the y direction equals may, and the net force in the z direction maz. And so this is general for all 3, and if you only have a one-dimensional problem or two-dimensional, then you just use 1 or 2 dimensions. So a thing to note is that if the net force adds up to 0, right, so if the net force is 0, then that means the net force in the x direction, the net force in the y direction, and the net force in the z direction, all 3 of those have to be 0. And then related to this, if the acceleration is 0, it means that the x acceleration is 0, the y acceleration is 0, and the z acceleration is 0. Right? If the net is 0, then that means the net in x, the net in y, and the net in z all have to be 0. And so this brings us to our third of Newton's laws, and this law also has a lot of different ways to be expressed, or you may have seen it. The basic idea here is that anytime an object experiences a force, that object exerts the same magnitude force on the applying object as but in the opposite direction. And so sometimes you may have heard this as every action there's an equal and opposite reaction. Sometimes Newton's third law is known as the action-reaction pair. The idea here is that forces come in pairs, and so if I push on this block to the right with some amount of force, the block pushes on me with the exact same amount of force, but in the other direction. And so symbolically, we would represent that as the force of A pushing on B, for example. The force of A on B is equal to the same magnitude but opposite direction, the force of B on A. And so anytime a force is applied, there is an equal force in the opposite direction applied back on the applying object. So the force A exerts on B, the force B exerts on A, and then FAB equals minus FBA. So the minus sign here tells us about the opposite direction. And again, these are referred to often as action-reaction pairs. So you apply a force to the wall applies a force equal in magnitude back on you. This is essentially how things like jumping work. If you want to jump up in the air, what you have to do is push down off of the ground. So you push the ground down, the ground pushes you up, and there you have it, you launch off the ground. And so this action-reaction pair, anytime you have objects interacting, you always have an action-reaction pair.